Good afternoon, ladies and gentlemen, again, and thanks, Michael. The Costa Concordia, as Mike said, without a parbuckling, there was no refloat. So the main challenge was actually to see if you could parbuckle the ship and bring it up in one piece. Obviously, what is parbuckling? Well, it's an old sailing ship term where you parbuckled barrels over the gunwale when you were loading barrels. Also, when ships went aground in days of sail, they would actually put out the booms and they would use the weight of the barrels at a distance from the ship to actually give her a list and try and get her off. The largest parbuckling operation was in Pearl Harbor in the Second World War. This was the Oklahoma, which was successfully parbuckled. There were several others that weren't able to be parbuckled. So even though they were warships, extremely well built, very strong, and in a relatively flat surface in the port, the Utah still remains, and I think the Arizona is part of the memorial to that day. So obviously the Costa Concordia, a large ship, just on 3 football fields long, well over 100,000 tons in weight, 8 meter draft and 49 meter freeboard. So the lower section of the ship was a strong part. The upper section was there mainly to give you the volume of space that passengers and guests want when they're on a cruise ship and to relax and enjoy themselves. So what actually happened, she sailed from Civitavecchia, which is the main port service in Rome. She was bound up to Savona, right up in the northwest near the French border. Passing through here, the Isola de Giglio. It was not a well-known island before, but she became well-known. So some time after dinner, the captain wanted to show guests the island of Giglio. Friday the 13th of January 2012, late at night, winter, no one on the island was actually expecting the ship to come anywhere near it. They came in at this angle. They increased to full speed so they could maintain their ETA in Savona, and they altered course boldly in this location and struck the rock La Scola. Initially the captain said it was uncharted rock, but it's the #1 dive site in Italy, so a lot of people know about it apart from him. They lost power within 2 minutes. They were sliced open 57 meters through 3 watertight compartments, 3 watertight bulkheads, so 5 compartments were flooded. And they drifted north with the momentum, and there was a slight turn out into the bay towards the mainland. That night there was a very light northerly wind blowing, and the prevailing current actually heads off to the south. So they were blown down to the south and southeast with the current, and came back to rest right on the coast. That was taken by one of the islanders who was around at the time, and at this point in time they were starting the abandonment. So they had taken a bit of time to get to abandoning the ship. By the time the Coast Guard helicopter was doing the search and rescue, they were completely horizontal, 90 degrees. And then by the morning, the buoyancy had sort of seeped out of the lower compartments, and she had actually started to crush herself around the reefs. There were 2 reefs she was resting on. One was underneath the funnel, and one came out from this headland underneath the satellite dishes behind the bridge. What was quite amazing to see was that she was well balanced on those 2 reefs. So literally the weight distribution was evenly distributed along the whole length on these 2 little spars that were 97 meters apart. So quite miraculous that she ended up there and allowed the balance of the people to get off. Obviously they went out, initial reaction was to get the oil recovered. Smith and Neri were appointed. Neri's just on the mainland up in Livorno. Smiths have a good relationship with them. So they did the oil recovery, and the idea went out to what we're going to do with the ship. So they had an international tender, 8 consortiums put their offer in, but she was also pivoted on this underwater cliff. So if she did slip off those reefs, she was going into deeper water down there. And that would have made any recovery extremely difficult, if not impossible, but a lot more expensive. So at this time, there was no one allowed on site. It was a crime scene. While Smith were trying to get off the oil recovery, there was a search and rescue as well. So it took 3 months before they allowed the tender to go out, and the tender was awarded with still no one from our team having been on board. So you have to make a lot of assumptions. Basically, assumptions are something that surveyors are not meant to be doing. You're meant to be using facts and interpret the facts as you see them. Some assumptions can get you into trouble. We knew how big she was. We didn't know the damage where she was resting on the rocks. The port side damage you could identify because that was actually outside, clear on the port side. How big was this? Well, I was appointed by an American-Italian company. So for the Americans, you got the Statue of Liberty, a Boeing 747, Chicago train, and a Hummer. If you stick her up, she's actually really big if you put her in New York. And we spoke about the Titanic, so these modern ships dwarf the Titanic and make her look tiny. So the main two challenges we had were the size of the Concordia, her structure, being a cruise ship, and her location. And that was what we had to deal with. We were the only consortium who said that you could actually refloat her in one piece. There were times where we weren't sure whether that was the case, especially when we stood on it for the first time. So basically, this is the valley between the two reefs that she's resting on, 97 meters, and at this maximum depth, 25 meters on a slope. So we're going to fill that with some sandbags and grout cement. Doesn't look too difficult. A bit close up. Some underwater platforms. These are offshore platforms that have had the legs adjusted for the slope. You put these underneath. So you pre-drill some sockets into the granite, and you come and put these down inside. And then you've got something to support her and something to rest her on when she's upright. Then you use some armbands or sponsons. As you'll notice, there's a grillage only on this lower section of it, because this is a section on the lower side of the hull. There's no strength in the upper strength of the ship itself, so there's no point in trying to attach this upper part. So there's a big cantilever. That's the tall sponson was 11 stories high, 33.5 meters, and the shorter one was only 7 stories high. It had a footprint of 10.5 and 11 meters, so each one was a very large structure in its own right, divided into 3 separate tanks. It gave us a little bit of options in the buoyancy distribution, and also because of the depth. So when they were installed, this would be slightly underwater, or just that. So you've got to put about 2.5, 3 bar pressure in there to displace the water out the bottom sea chest valves. So it's actually a pressure vessel. Now most surveyors in the room will know that 2 bar over ambient, you don't want to be standing next to a pipe on a ship when that goes bang. So if you look at the slope, you've got the platforms in situ, the grout bags, you put on the armbands or the sponsons, and you bring her upright. The parbuckling forces, well, the parbuckling forces determined that this part of the ship would crash. It could not, the starboard turn of the bilge could not take those forces, especially on just 2 parts of the reef. So it was essential that we had the finish of the grout. Finish had to be as good as this raised stage or the table that Mike's sitting at, and that the forces had to be distributed well over 100 meters of the midship section of the ship to try and protect that. The actual forces were about 450,000 meter tons, plus minus another 100,000 tons for unknown quantities of water inside. So as it actually happened, this was our only work platform that we were allowed for storage facilities and fabrication, hot work. The port itself gave us absolutely nothing apart from the ferry berth, where we were allowed to take off our equipment and then bring it out to location. So everything had to come from the mainland ready to use, or on a barge that we could actually store alongside and then put it on. In the first 12 weeks of being awarded the contract, we had to do 200 engineered documents. We had 6 subcontractors in the engineering team from America through Italy, Germany, and for one of them, Ticon, this was about 2 years normal work. They specialize in offshore fabrications, for E&I, SciPem and micropy. So this was round-the-clock engineering, but it wasn't to complete the engineering, it was just to prove the concept or engineer the concept to a reasonable degree that it was worthwhile going on. It also allowed us to identify subcontractors that could actually take portions of this engineering documents and give us a quotation, first on can they do it and how long it will take them to do it. So this was the fabrication facilities, the shipyards, the grout installation teams, the platform fabricators, and the divers. At the same time, we were doing an environmental baseline survey. The valley, this is the area of the ship itself. So we had to do it to the north and the south of the ship. And this was to give us a baseline survey of what the environment was like alongside us and how badly it had been damaged underneath us. We declared all the Posidonia. This is in the valley underneath the ship. So the Posidonia seagrass was declared dead. So at least we didn't have to worry about damaging the local Posidonia seagrass any further. That was all declared dead. And we found these giant Pini ignobilis clams underneath the ship. They about 1 meter high. They grow vertically or out of the mud. Very tasty, until we found out that they're actually endangered species and not to be eaten. So we had to transplant them, and when they've removed all the grout bags, they'll actually relocate them and try and re-establish some seagrass. If we look at the damage, as I said, on the port side, the side that was outside the ship, everyone could see that. But where she was resting on the reef, we had to make some further assumptions. There were 2 different local charts showing the different type of subsea profile of the rocks. So we weren't sure exactly the penetration inside the ship to actually keep her at that draft, or how much of the structure had collapsed in the way of the bow and the stern. Of course, we had a company called Overdick. Their speciality is finite element modeling, based in Hamburg. And they built a model, a 1 million point reference model from scratch. And then we superimposed that on top of the reef until we had the right, let's say, freeboard above the sea level. And that gave us the compression around the reefs. On the upper side here, you've got the aft section. That's right next to the engine room. So on the port side, you've got the initial cut that opened all the way through the port side in the engine room. The starboard side, you've been crushed up to 8 meters inside, so not quite this room, but very close to the width of this room that the vessel's crushed itself. On the bow, exactly inside of this area, you've got the ship's large theatre. The theatre takes 1,500 people, there's 3 stories high, and there's more than 50% of the beam of the ship. So on the starboard side, you've lost a lot of your longitudinal frame around that theatre, again with unknown damages. So again, assumptions. We used a finite element model called FS Dyno. It's normally used in car crash simulation. So what happens when you see those car crashes on TV, then they actually compare that with what the model would reflect. And from that point of view, they can actually prejudge what they can expect in car crash safety. Well, we used that over here. Initially, we had, this is the valley, we had 3 platforms in the grout. But after finding out the feedback, we had to extend 3 more platforms underneath the stern and a whole new section of grout. And this was because it said that the stern will most probably twist and could fall off in the parbuckle operation. So we had to support the stern all the way through the rotation and then give her 3 platforms to rest on. The bow said exactly the same thing, but the bow went into deep water, so we weren't sure what to do there. So we said, well, let's not bother about it in the meantime. We'll just carry on what we can do and still work behind the scenes on making some type of scenario planning for the bow. But here you see these small lines, if you can see them. That's the only area where the vessel was going to be subjected to all the force, was the midship section. If you had a 3D model, it actually looks pretty bad. We showed it to our client, but they asked us not to show it to the authorities. The authorities were already pretty paranoid and worried about this. And when we first saw it, we thought, well, that's what the model says, but it looks worse when you have it like that. So we kept that until the end. So we had to set up a structure to do a large fabrication project. We had 5 shipyards from Fincantieri around Italy, 7 fabrication facilities, 150 subcontractors. So we had to manage all that from the mainland. We were on a day rate, so we had to have a daily cost sheet. We had to have commercial contracts with all these people, monitor them, and then logistics to get everything delivered to site. On location, we had 4 teams, and those 4 teams would be completely independent but working in parallel, so we could all try and achieve the objectives at the same time. We divided Italy up into where the shipyards were, Trieste, all the way down the Adriatic, Palermo, Naples, Genoa. So basically as much as you can think of. We divided into 3 locations. We had a ship fabrication manager for every location and dimensional data control, because we had to make sure that all the fabrication facilities were working to the exact same tolerances. So every weekend we'd have feedback on the progress on the island, and then they'll be at the shipyards during the week to monitor. The parbuckling concept, as I said, is not rocket science. It's just more difficult in certain situations. So this was a point that we were worried about was going to crash. We've got the pulling system right on the outside of the sponsons, and that gives you more of a lever. And we go to the outside of the platform over here. Because of the damage on the starboard side, we said we can weld this little section of the sponson on the port side. The starboard side, we're not going to bother about that. There's no way we can actually try and find enough strength in the way of the reef or the ship after the parbuckle to support sponsons. So we said, well, we put large chains from the port side on these anchor foundations underneath the hull, and just to clear the starboard bilge. And when we parbuckle the ship, that will be underneath. And we'll have 56 chains from the bow to the stern, and that will be like a harness. And we'll sink the starboard sponsons, shackle them on, and then use it to actually pick it up. So almost like building a life jacket around it with the straps being chain. Also, we'd have to reinforce the turn of the bilge on both sides and try and spread these forces as much as possible to avoid the collapse. There was another website running at the same time, Anders Borkman, and it was called Why the Concordia Cannot Be Parbuckled. So he had pretty similar information. So, and he said P will collapse. It's just not going to happen, right? It was interesting that he came to the same conclusion, but a bit disappointing that the whole ship will break apart. So this was a live blog. Had a lot of people contributing, a lot of engineers and mariners around the world, and none of them were really positive. So it gave us a bit of a double check. You know, we had the vessels and the underwriters, consultants, double checking us, and we also had the website. So as I said, the onshore team was divided into 4 teams. So we had the inshore, they would be doing the initial landscaping, holdback systems. Nearshore, that would be the large dive team doing the grouts underneath the ship, the belly of the ship. Team number 3 would be on the Concordia itself. So initially remove the rock and then start preparing the ship for all the stiffening that we had to do to allow her to carry the weight of the sponsons and then to survive all the parbuckling forces. And team number 4, they would be on the weather side, the offshore side, and they had to do the large diameter drilling. And the large diameter drilling was for the platform legs to fit in. So when you're drilling at an angle on the slope, you know you've got a problem. It's granite, so it was very hard, between 105 and 120 MPa. And the diameter of the drill was just on 2 meters, 74-ton head. So that was going to be a problem. This is the inshore team. So basically their objective is to cut away some of the rock and build a small platform for these inshore anchors. And that would be used first to hold the ship in place while we carrying out the work, and then secondly to withstand the parbuckling forces and stop the ship going over the edge. So we needed 11,000 tons of holdback capacity on the inshore side. We called it landscaping because breaking rocks and blowing it up was not environmentally friendly, but landscaping is better. Team number 2, they lived on this the large dive team, and they had the foundation grout factory. So there was 120 people living over here. And then the supply vessel would come every 3 to 4 days from the mainland with fresh grouts and all the other supplies that we needed, the fabrication, steel plates, welding rods, etc. This is the offshore team. That's the residue of the rock. It eventually 12 meters in length was buried inside the engine room, 96 tons. We had to cut it up in 3 sections to get it out. This is the start of the cut, so it's 57 meters, you can see. And this is on the turn of the bilge. So as she was doing a high-speed turn, it just sliced right down to the keel, which was very sad. Team number 4, this is the large diameter drilling offshore. This is the drill head and the spread that you need to carry out this operation. It's much bigger than anything I'd come across before, and causes a few challenges. Here again, this is the hullback anchor. They've cut away this whole profile. We've got the anchor on the flat bit of rock, and we have these micropiles going down 8 to 16 meters, depending on the core samples. And this is 1,000 tons of holding capacity per anchor block. These core samples actually cause us a lot of problems. You get ready to the good core samples and you get lots of crap and everything in between. We needed good core samples to support the design of the anchor block. So when we found some weathered rock or some other sort of void space where there was sand, we had to go through that and start the 8 meters again. So some of them we had to go to 24 meters just to get 8 meters of holding capacity. This was the arc inshore if you're looking down. And the reason that was arced on the specific line is that every anchor block had to be matched up with the internal web frame of the ship. And this was the 16-meter contour. That was the maximum depth we could actually operate from the barge from the surface in that location. So that's how that was dictated to us. Unfortunately, if you look at the geological setting, we had 2 major faults that came down the mountain, and they ran straight underneath the sea and impacted on that anchor block location. We had secondary faults that also came across and impacted on another 2. So these all added to the work scope and complications in time. You had traditional boulders and blocks that have fallen down over the centuries, debris fields. So to better explain this to the authorities and the clients, we brought out a geologist, and he took us above the land, and this is a typical profile of the rock that you have underneath the ship. So you've got this carapax, so it's the last bit of volcanic lava that cooled, and then you have this interface between the carapax and the bedrock, and this is all rubbish. It's like the onions peel on an onion skin, so you've got to get through the skin before you get into the onion. So that's what we were expecting to drill in offshore to secure the platforms. So here we got the valley where the 3 platforms are. These are the 2 reefs. And this is a big drop off. Those are the inshore anchor blocks with the ship superimposed on top of it. So by this time we knew that we were in, let's say, bigger trouble than we expected when we won the contract. It took a long time to get the funnel removed. It was a state prosecutor, so you were not allowed to cut anything or remove anything from the ship without a permission. So we were doing a lot of work around that, but it took a couple of months, and then they said we have to keep it in case we have to put it back. So we had it on the mainland in a warehouse until she reached Genoa, when they realized that she could make it to Genoa without it. But that's the type of working area you had, with a rock profile very close to you. This is the landscaping team, so they've got an excavator that's been modified. It's got a root canal drill bit from a dentist, and then you've got the flat piece, the grinder. The environmentalists didn't like the look of that one. But of course, because the accuracy had to be pretty good, we had these small templates that the divers would put on the seabed with the survey equipment. We'd have an ROV watching the actual operation on behalf of the crane operator or the excavator operator, and everything had to be measured to be within tolerance. So here's the toothpick going away. He's cutting into the rock, and he cuts away this whole profile, and now he's going to work his way back. and make a ledge. So basically that ledge is about the size of a normal king-size bed, about 5 meters in length, 36 tons. The actual height of the anchor block, here you see it. It's all high carbon steel, 83 millimeter thickness. So a very solid mass. And it's got a slight angle over here, and actually the shear will actually cause friction to take up that last bit of holding power we needed. Again, each hole had an individual number, and that number coincided with the core sample, so we knew how deep each micro hole had to go. This is the divers putting it in position. So you can see here's 2 of them facing the ship. The center line of the anchor block had to be lined up with the web frames on the internal frame of the ship. And this is a survey equipment to measure the actual list roll pitch. The micropile team, they actually, first time they'd ever worked on water, so we put their micropile system on top of the small barge, life jackets, and told them this is it. They wanted more space, but that was the way they had to work. So they would come around and follow the landscaping team. The landscaping team would then position the anchor blocks, and the micropile team would follow them. So they'd start down by the bow and then work their way up to the stern and just install the anchor blocks and then do the micropiles and set them. These are the micropiles. They come in 8-meter sections. So as I said, you had 8 meters of holding power we needed, and you could go 8, 20, 8, 16 or 24 meters depending on the geological core sample. Here was a test grout micropile. So we needed 1,000 tons per holding capacity per anchor block. That was 100 tons per micropile. And here we ran out of pudding power at 270 tons. So once you're in the granite, it's fantastic. It was just to get into the granite that you couldn't get the operation going. On top of all these anchor blocks, you're going to put towers. And on top of the towers, you've got these strand jacks. And the strand jacks are the actual pulling force. So the blue ones are 500 tons. And that gives us a vertical pull of 500 tons each. The wires would go around the anchor block trunnion and then off to the ship. So once we got these already in La Spezia, they're all tested and tested, we were already on site with the anchor blocks, and we brought them out and installed them. At about this time, we were told that because no one knew how to tell us we were doing the right thing, they said we have to comply with the Italian Code of Offshore Structures. It's used in the offshore industry for platforms and semi-permanent structures. And the opening paragraph said you have to submit your drawings 2 years before you start the project. So we worked in parallel to comply. One of the things we had to do was to get them in a vertical tolerance of less than 3 degrees. So again, you see the divers, they're working on the anchor blocks. They're actually putting shims between the anchor blocks and the towers to get this 2 degrees of vertical tolerance that we had to comply with. You can see very good visibility. So every diver had an ROV watching them. And from that ROV, we get a global view of the work site. The standby diver could actually watch it. It sped up and made a whole lot of safety factors go away. The grout team, so the mustard color that you see here, that will be the grout. This was the initial profile of the grout, and then we added the 3 baby platforms at the stern. As I said, very large volume, just on 23,000 tons, with a grout factory put on the barge, and along with the diving team. So we had all these grout bags that would be fabricated geotex grout bags, and they'd have these different layers of baffles inside, and you had different shapes. So you'd have pyramid shapes, triangles, mini bricks, large bricks, and Kit Kats. And that would actually help you, when the diver would go down, he said, send me down some triangular bags to actually try and change the profile of the slope of the seabed. Each grout bag had to have a specific number, and all of the recovery strops had to be certified with a file kept with the grout bag number, the file certificates, for someone to look at someday. One of these grout bags is the size of a swimming pool at a house, so between 45 and 80 cubic meters, depending on the profile of the bag. But it's a lot of grout to do over 1.5 football fields. So here you got the grout, the mountain or the wall of grout And this is the offshore drilling team. And what will happen is once the platforms are installed, there will be a bumper, and then we could do the final phase of grouting to tie it all together. This is what it should look like. You can see the profile of the seabed. We've got the platforms all beautifully in place, the grout at the stern, a little profile to support the stern. And these are the KitKat bags. And KitKat bags caused us a bit of problems. I didn't understand what we were doing when we ordered them. And so we took a picture of a bar of KitKats and we said we want these for all the chains so that when she power buckles, the chains will fit right inside the slots for the KitKats. And they came out with that. So this is at the stern again. You can see the profile of the grout to actually support it all the way through the rotation and then onto the platforms. And you can see a bit of the slope on the seabed. So this is what became the big challenge, was to get the vertical sockets drilled to allow these platforms to be fabricated around Italy, and when they arrived on location that they would actually fit in the sockets. Here we have a diver that's got to be, he's working to relocate the grout hose. So he's down at the same sort of depth as the top of the platforms at about minus 32 meters. He's got the unenviable task of pulling the grout hose from one side to the other. And the last thing he wanted to do was to get a blockage in the grout hose, because it could take you 2 days to actually remove that and rerun a new grout hose. So we watched everything. I'm not sure you can see the strings. This is the profiles that they had to work to with the profile of the grout to actually get the grout in the right profile for the parbuckling. On the Concordia, so we had to wipe away all the paint on the web frames, and we put doubler plates to stiffen the ship's hull. And on top of the doubler plates, we had these anchor blocks. And the anchor blocks would be twofold. One for the to hold the chain, and secondly, to put the sponsons on. With a heavy lift ship, we had to have a stabbing guide and something to keep it there. Release the heavy lift ship, and then the welders could get going to weld it. So that was like a wedge that the sponsons would clip onto. All the welders and everyone on the Concordia had to go through a mountain climbing course. The angle of 27 degrees is pretty difficult, in fact almost impossible to work safely. So we had the Dolomiti Mountain Rescue Team involved on a 24-hour basis. So firstly to train everyone in the equipment, and then to monitor them and make sure they were clipped in. Every welder had to be coded. We ended up doing 100% NDT in weld inspections. We couldn't allow anything to fail. Unfortunately, under the Italian Code of Civil Offshore Structure, there's no code for this type of welding, so we couldn't actually qualify with the code. So we had to develop our own welding procedures to actually get that accepted. That was accepted also after the parbuckle. You can see this is where the rock was. There's quite a large chasm into the ship. So we weren't going to try and close up the ship. The ship was going to be completely waterlogged all the way through the parbuckle and the refloat. There were just too many cracks and holes to try and seal it. These were just construction patches to actually take the weight of the chain through the parbuckle so you didn't cut through the ship. So just nothing to do with watertight integrity. And these are the doubler plates we put on the port side. So it was 9 meters in length, 1.5 meters wide, and 40 mil of also high carbon steel. And that would actually take, the chain had to be dead center on these doubler plates to spread the load as all the way around the turn of the bilge. So here you can again see the welders welding the port side. As you get towards the bow, you know, the difficulty of welding, you're almost standing up vertically. So you had the younger guys would do that type of operation. The more genteel 27 degrees was for the medium-aged welders. So the port side, we could actually quite easily put the doubler plates exactly on location. On the starboard side, we had to make sure that we installed them in the right location, and then that the chain would be in the middle of that. So we built these semi-hawse pipes, like anchor pipes, on every doubler plate. We'd go down and just have small pad eyes. The divers would use turfers to get them into position. And then we'd finish the grout run. And when all the grout was set and cured, after 7 days of curing, then we could run the chains. These chains are quite heavy, and we didn't want to knock these out of position. We had 56 different chains to run under. Each chain had its own container, 370 kilograms a link, and 133 millimeter or 5 3/4 inch chain. Between 28 and 30 tons per run, depending on which part of the ship the chain was going on. The best way was to tell the divers, just put in your chain and don't tell me your problems. So here you get a cutout with the chain run from the anchor block going down to the hawse pipes on the starboard turn of the bilge, and then the bell mouth would allow it to be the messenger to actually guide the chain. And then when she was parbuckled, then this would be outside, and you'd use that for shackling on the starboard sponsons. Firstly, we had to, before the first winter, we had to make sure the ship didn't get moved off. So we needed 4,000 tons of holding capacity, and we used the first 4 anchor blocks to do that. If you look at these pulling machines and the amount of wire, each one has 18 individual wires. So that's, you need a 100-meter barge to prepare the wires on the strand jacks before you can actually run them. So you just run a messenger with a diver, and you have another crane on the inshore side, and it's like a piece of dental floss. You just work it back and forth until you get the chain and the strand jack wire in position, and then set down the pulling force. So the first 4,000 tons of pulling machines were on the outside of the ship because we didn't have the towers installed on the inshore side. In total, 172 strand jack machines were used. We did try and buy them at the beginning, and they were told that there was be a day rate contract. The last 106 only went back about a month ago, so it was a very nice contract for the Italian supplier. Large diameter drilling, I said 2 meter diameter. This is a drill head, and this is a drill bit. So it's got all these sacrificial rollers, or rollers with tungsten carbide teeth, and just uses the weight from the surface to try and get into the rock. So all of the drawings we could find about this was on a flat bottom sea. There was nothing with trying to explain to us how we're going to do it at 35 degrees. We had to do it in a closed system, so because of the environmental sensitivity, we had to have a conductor from the surface down to the seabed, and then all the cuttings that are cut away have to be sucked up inside, put through these vibration desanding units, and then the cuttings disposed of as hazardous waste to shore. The island actually wanted this. It was beautiful white, same as their beaches, but I think they had to buy it back. So these are the conductors. You can see it's a very high wall thickness. It's going to take all the drilling loads, and this will be from the surface. The drill head will go down here until we get into the seabed. So again, this one is what it looks like on a flat surface. We didn't have a flat surface, so we had to guarantee that we could actually drill these sockets into the granite at all different angles, so that when the platforms arrived from their fabrication facility, they would end up going into the right location. We had a moving platform on the surface. It was about 60 meters from the water down to this rock. So if you have a very long drill bit on a hand drill, and you want to drill a hole into a mirror in your bathroom, and you just put it at 45 degrees, you're going to see what's going to happen to your location accuracy of drilling that hole into the mirror. So we had to build these subsea templates. This is a template, so it's got a 6 meter sleeve. These hydraulic legs that can be adjusted to actually take up the profile of the underwater bathymetry, and then that will hold it in situ and try and allow us to stabilize it while it gets into the rock itself. That's for the baby one. The bigger one obviously had 6 legs, so it needed to be 6 times bigger, 285 tons on its own, with even longer legs because of the size and distribution. So the 3 large platforms were the size of a rugby field or soccer field. So it's about 45 by 35 meter footprint to actually hold these sleeves. If you could maintain the horizontal accuracy, so if you could get the template to be within half a degree of tolerance, then the sleeves would be in vertical half a degree of tolerance, and that's what we were allowed. The good news about this closed system, the environmentalists were worried that apart from the turbidity and the cuttings, that the noise would chase away the fish. But every time we started up the drill, these 2 meter, 3 meter long tuna would come around and get vibrations from the drill head. These were also very tasty. We could eat these. So that was a bit of a bonus. So these are the installation of the baby platforms. And now we come to the big ones. So these were built in the Adriatic, roughly 1,000 tons of steel each. This is a bumper on the front that's going to hold the grout foundation in position through the parbuckling. So you could get 2 onto a large barge. And you'll see there's about 25 meters to the top, 35 meters across, and 40 meters in beam. When we came to do the installation, of course, we were a bit nervous. We had been well behind the schedule on the drilling operation, so there was a lot of, let's say, eyes watching us. At the moment, nothing's happened on this location, so from the authorities' point of view, nothing had happened in 6 months. It was all happening underground, though, but they couldn't see it, so we could take a battering for this. This was the first main structure that would go in. So we had 7 ROVs, 6 to each leg, and 1 that could float around. And every ROV had a monitor by the crane operator, and we could actually install it with adjusting the cranes to actually get the legs in. It went very well. Here's one ROV watching another one. Very useful machines, very portable. We could average about 130 hours in the water before you had to change the first spare parts. So that was also quite useful. But the platforms went in, fortunately, without any major problems. Life on board the Concordia, this is the actual lifeboat deck. So you can see the angle that she's out of tolerance. This is a false platform we built, and that's our only walkway, only horizontal walkway on the ship. So for all the welders, fabricators, and the team on board the Concordia, that was their tea break, their workshop. They use it to house all the equipment, keep it shipshape. These were 3 different workshop stations every 100 meters, and then the welding station. So we could use 10 welders per station. Each welding station had 6.5 kilometers of welding cable, and then a safety team to monitor them all. So the sponsons, as I said, these are pressure vessels, roughly 3,600 cubic meters per tall one, and they're going to be laid in the midship section, built at 5 shipyards in Fincantieri around Italy, all to the same tolerance and dimensional controls. And again, because of the 2-bar overpressure, it's quite a solid tank, so much stronger than any other ship's tank that you'd normally worked with. To make sure that we could actually deliver on location, we said if they can do the basic fabrication at Fincantieri, we'll do the final outfitting and installation of valves and control systems ourselves. So once they were ready, we'd bring them around Italy to Livorno, bring them ashore. We had to rotate them so that we could do all the welding had to be top down, and cut out this profile on the grillage, and that would fit onto the reverse profile on the ship's side. So every frame was profiled about 3 or 4 days before they were loaded out, and then they would just make sure that these cuts were as close to that profile as possible to reduce the welding throat. This is about 540 tons. So again, we had a lot of heavy lift movements and load-outs and skid-outs. Here we come to the installation of the first one. Again, the weather had to be good. Once you put it on board, it's still going to take you a couple of hours to cut the shackles. There was no way you could undo a shackle that size at that height. So all these shackles just had to be cut and sacrificial, one-time use only. That one went okay, but if you look at the level from the water, it's about 500 millimeters or half a meter. So once we put that on board, then we'd gone past the point of no return for the parbuckle. We had to go ahead and parbuckle. So we went ahead with P11, and this would give us the dimensional tolerance along the length. This is where the welders would spend a couple of months. P11 was only 7 stories high, so you can see the difference. And of course the gap between them is 38 millimeters. So it was actually quite a tight tolerance for us to, it was essentially we had the profile and the grillage correct to make sure that that fitted. That was another major milestone after the platform, so we could have another braai or barbecue. Where this time we're looking for any excuse to smile. This is the horizontal ones that we're putting over. So where the damage in the bow and the stern section was, we'd have these horizontal ones to actually distribute the buoyancy more for the refloat. On the port side, we could put it on beforehand, but this welding profile on this vertical section proved quite difficult. What do we do with the bow? So by this time, we'd worked out that we had an idea or concept called the blister tank. So we take out the 3 bow thrusters on the ship, and we put in these pink or green pipes, large diameter pipes. They were big thrusters. We'd bring in these like a neck brace. So if you see a paramedic's neck brace that they take on to a sports field or a car crash victim, that's exactly where we got it from. We had a couple of paramedics on the team, and everyone that ended up being flown off by a chopper had to be secured in a neck brace as well. So you sink down the neck brace and you wrap it around these the pipes, and then install it and suck it on. So you get a little bit of force being held on by the pipes, and then the rest would be the hydrostatic resistance as you go through the parbuckle. But the reality of the situation was, first we were told it was crazy, it can't be done. It's a large volume, 6,500 cubic meters. It's bigger than my first cargo ship I went to sea on. To find that steel, to actually design it, fabricate it, deliver it on time, people were a bit nervous that we didn't have an installation procedure when we started with it. In fact, it was about this time that we did some last-minute modifications to the hinge to try and give us some resistance for the installation. So we actually had 2 different hinges. The top one would give full rotation, and the lower one just allow 5 degrees of the starboard sister to rotate, and then we think we could install it. So she arrived on location. Again, a 1,500 ton lift. The last bit of buoyancy control systems. So there were 3 different tanks on each one, and because of the profile and the shapes of these tanks, and we decided that to control the buoyancy, the tank was either full or empty. There was no way we could actually control it as it went through that water column into situ. So now she's in the water, the one sister's down, and we're bringing in location. This was our control room, so basically we had ROVs, winches, and micro cameras which were watching every part of it. It took about 3 days before we got her into position, and we cut off the lower hinge, and it was about 4 or 5 days later before she was 100% installed. Simple. So the environmental protection, Giglio is a summer tourist island and gets about 85% of their revenue in those very short summer months. So just from a cosmetic point of view, we had to have oil booms around the island, even when there had been no leakage of oil. Although the weather that they told us not to worry about did pick up. This was the first winter we had. The Halloween storm was the first one of winter 2012, and the ship actually collapsed 2 meters that night. So we had to then go and cut the platform legs all 2 meters and change the drill sockets in the bedrock, but she actually collapsed pretty much in parallel. So it was just the lighter structural members that were collapsing, not the main frame. Water spouts, these are never seen in winter, but there they are. And then this is the rocket La Scola. Beautiful coral, very tasty, some of the best tasting octopus I've ever had. And then we had mascots that came and joined our team and wouldn't leave. So now we come towards the parbuckle day. We've got all the sponsons installed. You can see that with the collapse of the ship, that gap that we had near the midship section on the bow, the actual sponsons were touching the sea. So we had to get it over and done with as quickly as possible. This is a swinging platform so that the hydraulic power pack and generators would be horizontal all the way through the rotation, and we wouldn't run out of power. Everything had been pre-checked, and we wanted to start on a Friday. Everyone said no more Friday work. And we started on a Saturday. They said no one starts on a weekend because the authorities would rather we start on Monday. So Monday the 16th of September came. You can see from the drone, there's the bow blister, the two horizontal sponsons in the way of the damage, and in the midship section where the pulling forces would be. So we pre-tensioned over the weekend, and that is always good to pre-tension a ship. So you set up a vibration, you're testing all of the, let's say, the anchor points nice and slowly over that weekend. There was just one last thing to do, and that was to kiss her keel goodbye. And then we started with the parbuckling on Monday the 16th. You can see from the weather, the clouds are coming down from the north. We had a bad weather forecast compared with the weekend, but that was the secondary condition, or let's say factor. Later on in the day, you'll see that the weather comes from the other side, and then everything in between. So what happened was that because everything had been based on assumptions, no one had been inside the ship, we didn't know exactly how the water would flow through. So you imagine this room being completely filled with water. There might be a couple of air bubbles. So as we rotate, all the water has to move through this door and be replaced with water coming in through the other windows and doors. So you'd have a sort of hesitancy of forces. So we had an optimistic weight assumption and we had a pessimistic weight assumption. We went past the optimistic weights assumptions and we got to the pessimistic weights, and we went past the pessimistic weights. But we did have another spare capacity in our pocket, and fortunately once she actually broke off the rocks, then it actually did follow the curves. The first 10 degrees of rotation was when we expected the turn of the boat to collapse. So that first 10 degrees was pretty quiet. People were a bit nervous. Then as she got past that 10 degrees, the forces started coming down, and we got more and more sort of optimistic as the evening went on, until the morning when she was parbuckled, and you could actually see that damage that came out of her. She was pretty much like the 3D drawing that we had, and over the whole length of the ship she was 1 meter down by the bow and about a meter, just over a meter to port. So she had a port list of 1 meter and a trim by the bow of 1 meter, which was better than we hoped. This is the absolute deck that's been crushed. So as she actually slid around the rocks, and the rocks actually held her in situ through that winter. We had a search and rescue break then because there were still 2 bodies missing. So we had 3.5 weeks with the search and rescue teams trying to locate the last 2 bodies. One we found, so that meant that we still had to try and find the last one either during the preparation for refloat or after refloat. The doomsayers continue. So the same website that said it can't be done said that actually when it did parbuckle, there was so much noise and underwater, let's say buckling and collapse, structural failure, that actually the ship will never be refloated. So he obviously knew more than we did about what was happening underwater. Here we put a tower crane into the swimming pool. It had a 60-meter boom, and this really sped up our operation over the winter months. Although they did find that under offshore construction regulations, you're not allowed a tower crane in a ship. So they asked us to take it away. We said we couldn't. It's still there today in Genoa. So the starboard sponsons we're going to install in the vertical orientation, and we're going to put them in the water, sink them down, and then shackle on the 4 chains. So each one of these is going to be another strand jack that will then tension up the chains, and then would deballast the sponson. It was more difficult to do it in this vertical situation. We didn't expect people to have to get up there, and that's about 56 meters off the deck. So it's a long way to climb up to test your equipment. We had 157 kilometers of strand jack wire that was used. So it was everything available in Europe and America was brought over. Now, this is what the profile of the port side should have been. So we're going to sink the sponsons, and then it would actually rest on the sort of hull plating. And you would just have the main decks where the balconies were, and that's where the interaction with the sponson would be. But we knew that there was massive indentation. So we said, well, what we'll do is we'll cut away all the damage in the balconies, and we'll put some false bumpers out of those decks. So where you have this balcony over here, we cut that away and we replace it with a false bumper coming out of the deck. And these are the bumpers sticking out to hold the sponson so that you had the same geometric alignment all the way along. Of course, the welders thought they had finished welding, but we had to then tie the upper and lower decks together. But we got a nice finish. You can see that the bumpers worked out for salvage, not bad. So now we come to install the last sponsons. This crane barge came from Holland. It was absolutely perfect for what we wanted to do. We had another 17 heavy lifts, and she fitted just between the towers, this rock over here, and the ship's hull. There's about 500 millimeters of gap. Sometimes she touched the rock. We had an ROV underneath there, and we could explain to them that it wasn't major contact, it was just kissing the rock. I think it was from Shahid, keep it kissing, right? They were a little bit nervous. There was brand new crane barge. The underwriters did come out to also have a look, but it was too late anyway, we weren't taking her out. So this is a horizontal sponson coming in. Now that's the length of the tower to hold the strand jack above water. So that's the depth from the surface of the sea that this has to be lowered before she's approaching her baseline. So this is all the strand jacks and the sponsons installed on the starboard side, and you'll see that they're at different profiles, and that's still because we have an impact from the reef. How do you connect a 600-ton shackle to the chain with difficulty? So over the winter we had these manufactured, designed and manufactured, and then the divers would install the yellow piece, the male section, to the chain, and we'd have a messenger that would be pulled up into the sponsons, and there'd be a female receptor that would just close behind this strong point, and that could give us 1,500 tons of holding capacity. So that meant that instead of having divers trying to connect the chains for hours, we just have the messenger being connected by the diver, and about 15 minutes later that sponson was 4 chains were connected. So that really sped up the operation. So now we come towards the end where we installing the very last sponsons, and we're coming up to the July. The target was to be out of there before the August holiday season, and this is the last sponsons going, and that's going to clip onto the bow blisters. So before we did the blisters, the bow blister tanks, we weren't sure how to install the bow sponsons, but having a bow blister tank there, we could just shackle it on, clip it onto the blister tanks. We still had this interference over here from the reef. So these are at their baseline survey. This is where we need them to be, and these ones we actually can't get there. So we had to refloat the ship by about 2 meters, move her 30 meters offshore to get away from that reef, and then we could do the final connection of the final chains and get the sponsons re-situated to the baseline for the refloat. We had an average of 530 people on site. It's a large team. 55 coded welders working on shifts 24 hours a day, 130 divers, 22,000 individual dives. So even though every diver was qualified under IMCA standards, we did surface decompression. We had 11 chambers on site, but 22,000 individual dives is a big dive operation. We had almost 23,000 tons of grout cement, 33,000 tons of steel was used in the fabrication of the platforms, the inshore anchor blocks, the towers, the sponsons, and this you could actually build a super tanker with. We had 1,000 pages of software programming written by a robotics computer whiz kid that we found, and that was to coordinate all of the compressors and the refloat. So we had the hydraulic pulling machines on the strand jacks, we had the compressors, the generators and hydraulic power packs, and then we had the sensors on each tank. We had 150% redundancy as well. So where the rocks were there, we had 2.5 times redundancy in the midship section, just 100% redundancy. So it was a very powerful system that we used for the refloat. When we got her off, we knew that the prevailing current is from the north to the south, so we put out a big lazy anchor spread, and then we were going to refloat it and let the current just tension up the mooring spread. There was no way we could pre-tension it and move the ship into a position. We had no winches offshore, so it was just a lazy anchor and let the current do it. What they were worried about is that the current might take it back to the initial rock. And we said, well, it shouldn't. So now we come where to explain the actual refloat operation. So what we're going to do is we're going to have a lazy subsea mooring system. Oops, fingers. Yeah, so we're going to refloat the ship about 2 meters, move her offshore until these lazy ropes, these were 30 meters longer than expected or necessary, and they were tied to the chains on the base of the keel to the towers. So when they were tight, we knew that we had cleared the reef. The tugs would hold it live boating, we'd bring down the sponsons, and then we had full control and we could actually bring it up 1 deck at a time to let the water run off and refloat the ship. So basically this next one is about a 3-minute summary of what we did in 30 months. So basically, ship salvage is a science of vague assumptions based on debatable figures from inconclusive instruments, performed with equipment of problematical accuracy, and persons of doubtful reliability and questionable mentality. Everything appeared to be impossible, and then it's done. Thank you.